Yeah, well, we'll do it together. I'm Tim's co-conspirator. My name is Anton. We're gonna recap some of the computer vision stuff using your favorite software, which starts with Mod, but it's not Maple, it's Macaulay 2. So is the font visible from the back? Okay, all right. So
yeah,
maybe that's great. Yeah, so a camera for us, one important example of a camera is just by 3x4 matrix, and I'm just generating a random camera here. Suppose I want to take, this is perceived as a map from P3 to P2, linear projective map, and I would be mapping points in the world. Well, here they're denoted by capital X. In Tim's talk, I think they were Q, right? We're mapping them to the camera plane, which is P2, and obtaining 3 vectors there. Now, if we want to dehomogenize them, that's what people in computer vision usually do. They mean a particular affine chart. They just divide by the last coordinate, and I'm just going to define a function in Macaulay 2 that does it. Okay, so let's continue with this example. Suppose I generated 5 points in the world in the affine chart. So each column is a point. There are 5 points. I could attach one more coordinate to them to make this coordinates homogeneous. I can apply my map to get 5 points in P2. I could dehomogenize them to get them back in the affine chart. And my goal is to recover A that fits the given small x, the projections onto the camera plane, given the big X, which are and also given the big X, which are the world points. Okay, so what can I do? Well, first of all, we did discuss, so Tim discussed in his talk that there is this problem, PNP, a classical problem, and you have to do a bit of a dimension count to figure out when you have as many equations as unknowns. And this part describes that. But for all practical purposes, we would want to work with matrices in SO3. The cameras that are calibrated are given as elements in SE3, special Euclidean group. So we would probably need some kind of efficient parametrization of SO3, and Cayley parametrization is one of them. So you can define this map going from small SO3 to big SO3. It's basically mapping skew symmetric matrices into matrices in SO3. Okay. Well, so how would I set it up? How would I set up the problem of recovery of my camera in Macaulay 2? Well, so here we're going to work over the field QQ, but it's not important. We have to introduce all of the ingredients in our ring, in a big polynomial ring, and probably define a fraction field of that to make sure things are invertible. Well, we know that P3P is actually going to be a good problem, good minimal problem here. The number of equations is going to be the same as the number of unknowns. What I need to do is to first fabricate my equations, fabricate my data. I would synthesize the camera. I would synthesize, well, here I'm synthesizing something with small integer numbers. I would synthesize the camera by doing this operations, and then I get a 3x4 matrix. So this is a camera. It's in SE3, and you can do it. Can I recover this synthesized camera if I synthesize the data as well?
I think we have a question.
Yeah, question.
Is HP low rank interval?
Say it again.
Is H is rank 2? That's the problem. Ah, yes, that could be a problem. Not random enough.
Ah, yeah. Thanks for noticing. Let's regenerate that.
Random's not so random.
Yeah. So usually you're lucky, but sometimes you're not. That's how numerical computation goes. So if we redo this and then try to plug in the matrix with indeterminate coefficients generated the same way, right? So here I'm taking as Q-symmetric matrices. Now I have no way I can construct it of deficient rank because it's symbolic. I get the camera that is my calibrated camera. Well, next I'm just gonna use commutative algebra powers, which are very special powers. I could just think of introducing those depths that Tim introduced. Those were lambdas in his slides. Now they're called L's. And then I would equate the projected images to the projections. So at the end of the day, I would get a lot of rational function equations. I mean, these are, you know, they look impenetrable, but they're not that bad. If I want to equate them to 0, I would want to just extract the numerators and create a polynomial system, and that's where I get to an ideal. An ideal here is just, well, some ideal that we created. We would check the vitals, as we call them, dimension and degree. I should comment here that if you care only about the degrees and dimension, don't join our group either. I mean, David Hilbert computed those, and Ben Schoenfeld does it every day, I guess. But that's not the only thing we care about here. So what we care about in our group actually is constructing solvers for this kind of problems. And I would want to show you at least one way to solve this. I mean, you can go many ways about this very simple problem, P3P, but one way would be to try to reduce it to some kind of a smaller problem. I would eliminate everything but lambdas or L's. I would get a system of 3 quadrics, as Tim was getting in his slides. You can check that the quadrics that he got with the laws of cosine actually not hit granite, right? Yeah. In 19th century, they got them. So those quadrics live in this ideal, and you can try to solve it. You can do it in many ways. You can do symbolic decomposition here because the data is exact, but the fabricated data is exact. But you can also, as an exercise, study what this package does in Macaulay 2. It would actually solve the system for you, finding all complex solutions. It's called eigensolver. And notably, it has more commutative algebra in it than homotopy continuation. Just look inside. It's also doing approximation, but with a bit more commutative algebra. So you can do the sanity check. Well, let's skip the sanity check. You can skip. The sanity check would be to just look at what the numbers were supposed to be for the depth, the last coordinate here, and checking that those were covered as coordinates in one of those 8 points. Now we get into this problem of quartic or quadric. You want me to click through? You take over.
Yeah.
Okay.
Well, this was confusing.
So this is from the last talk.
So some people, I think, in the audience were confused last time when we were talking about quartic constraints on the camera center arising from 2 3D, 2D matches, because there are quadrics, as we saw in the previous slides. So I don't have enough time to go through this, but the link to this worksheet will be posted on the website later tonight, and please go through it and verify that you really do get a quartic. But I think I'll switch to my slides now unless there are any questions about this. Okay. Great. So here is this thing. Should do like view. Great. So that was the tutorial. I know we're all hungry, so I'm going to power through these last few slides that tell us about reconstruction problems. So we talked about resectioning and triangulation, where maybe you're given cameras, maybe you're given 3D points, but now you're only given 2D points. And so what can you do? Well, you formulate this again as inverting a rational map. So now it's a map that eats m cameras and n world points and spits out m times n 2D projections. And to even make sense of this recovery problem, you have to get rid of fundamental ambiguity here, which is the action of PGL4, which changes world coordinates. Okay, and if you would like to work with calibrated cameras, you can think about, okay, what's the group you should replace PGL4 with to properly formulate this problem. Okay, this is a rational map. We're interested in things like the graphs of rational maps. So what can we say about this one? Well, if we have m cameras and 1 world point, then the vanishing of this ideal of this graph is known. So this is something I worked out with my friends in Seattle, Samir Agarwal, Max Lieblich, and Rebecca Thomas. And it's generated by 2x2 minors of these matrix AI, Q, PI. So this is a 3x2 matrix. I guess these minors, Reese algebra people would call these the Kosool relations, something like that. So these are clearly in the vanishing ideal, but they don't actually generate a saturated ideal. So they're not saturated with respect to the irrelevant ideal in the cameras. So in order to attain a saturated ideal, you need to throw in these things called Grassmann tensor constraints, which I'll explain in the next slide. Okay, that's just for 1 world point, by the way. So this is something that we don't really know much about if you have more than 1 world point. So this is sort of like a universal multi-view ideal, if you will. And to appropriate the terminology from earlier today, I think this is like a non-gentle scenario, right? So we can say something kind of like silly about how to saturate and get the vanishing ideal. But already with 3 world points and 2 cameras, there are things that are not in the ideal generated by these Kosool relations or Grassmann tensor constraints. Right, okay, so let me say something about Grassmann tensors. Well, this is a pretty general setup. So if I have m projections from a world, Pn of dimension n, into images possibly of different sizes, so Pni, then I can basically do a linear algebra trick that eliminates the unknown world point and the depths by saying that this vector has to be in the kernel of this sort of big matrix. And so notice that the minors of this matrix are going to be multilinear in the 2D points. And so there'll be multilinear forms which have to vanish if this matrix has more rows than columns. And so these multilinear forms have coefficient tensors, and these are what Hartley and Shafalitsky in their paper called Grassmann tensors. And the reason why they're useful is because other than a few explicitly known cases, these generically determine the PGL n+1 orbit of a camera configuration. So in other words, knowing the Grassmann tensor in most cases allows you to perform reconstruction, at least in principle. Okay, any questions about that? Yes?
This really helped me. I want to ask you, the previous slide you wrote P11 and now you wrote Pn. What type of slides extend high dimensional space? It also projects high dimensional space to 6 to 5. What would and what would?
Sure, that fits into this framework.
This one is for FPN,
Yeah, any n.
but the previous slides, I guess.
Well, P11 was 11 is the number of degrees of freedom in a 3x4 matrix.
Only for this case, for the.
Oh, this previous term, this was very specific. Yeah,
Yeah, so this one we want generalized or we don't know?
I don't know. And okay, anything else? Good. Yeah, so we talked about the fundamental matrix yesterday. So this is just an incarnation of a simple Grassmann tensor for two cameras from P3 to P2. So you can verify that this nice determinantal identity holds. And if you're interested in more than two pinhole cameras, then you'll stumble upon quite naturally these things called trifocal and quadrifocal tensors. So again, they have a similar structure as this, just with 3 of these green columns or 4 of these green columns. And actually, things sort of stop with the quadrifocal tensor in the sense that all of the Grassmann tensor constraints will be monomial multiples of one of these 3 types for the pinhole camera. All right, so let me tell you a little bit more about the fundamental matrix, though. So let's say up to coordinate change, I have 2 cameras, and I could, using the coordinate change, I can sort of put this first one into standard position. That's true in the calibrated or uncalibrated case, as long as these are, full rank. Right. So I can expand this determinantal constraint, this Grassmann tensor constraint, using this special form. So notice I have a 3x3 upper identity block. So that tells me I should take the Schur complement of that block in order to reduce this 6x6 determinant into a 3x3 determinant. And you do a little bit of vector arithmetic identities. And what you'll see comes out is an expression for the fundamental matrix as the product of a skew symmetric matrix, depending on the translation, and the rotation matrix R. So this is a parameterization of fundamental matrices, T cross times R. So if you're interested in recovering the fundamental matrix, this is what Hesse did in the 1800s, at least on paper. Then you use this parameterization of fundamental matrices. So, okay, we have a parameterization of an algebraic variety. You'd want to know what equations vanish on it. Well, in this case, it's just the determinant. So any rank 2 matrix, any matrix of rank at most 2 is in the closure of the image of this map, vice versa. And so okay, rank 2 matrices in the projectivized 3x3 matrix space are a 7-dimensional variety. And therefore, if I have 7 matches, such as this one, P1, P2, it gives me 7 linear equations. I'm slicing the fundamental variety with 7 linear equations. And what I'll get is exactly 3 solutions. That's the degree of the fundamental variety. So that's the 7-point algorithm in a nutshell is doing this. So that's the uncalibrated case. What about the calibrated case? Well, here our camera matrix lives in SE3, so we have a similar looking map, different domain, and we could ask what the implicit constraints are. So we still get the determinant, but then there are these 9 other kind of funny looking cubic constraints. They're usually called the de mesure constraints. De mesure, somebody who studied this problem. And so these 10 cubics generate the vanishing ideal of calibrated fundamental matrices. And usually these are not denoted F, they're denoted E. We call them essential matrices. And the variety of essential matrices is now just 5-dimensional. So if you know that your camera is calibrated, then it's possible to solve reconstruction by estimating the essential matrix using 5 matches. And moreover, the degree of this essential variety is 10. So the way that people solve this problem is they compute the roots of a degree 10 polynomial and then recover rotations and translations from that. So essential matrices also have something to do with what's called epipolar geometry, and this is related to one of the problems that we've distributed to our working group. So if I have a fundamental matrix F, there are these special points called the left and right epipole, EL and ER. And so EL basically is going to span the left null space of F, and ER is going to span the right null space. So this is assuming F has rank exactly 2. So here's a nice question about epipoles is, what can we say about the constraints that a bunch of 2D point matches, so 2-view reconstruction scenario, put on the left and right epipole of a fundamental matrix? And part of the reason I introduce the 7 and 5-point problems is because this is telling us the range of interesting scenarios for this question in both a calibrated and uncalibrated case. And so in the uncalibrated case, we basically have an answer for generic 2D correspondences. And so I can tell you, for example, what this looks like if you have 4 2D correspondences. So 4 points in P2 are very special, right? You could fix them with automorphism, in this case, PGL3. And what that means is if you have a bunch of matches, as long as they're in general position, you can just make them equal, right? Just apply PGL3 to one of the views. And so then you've got 4 points, and you've also got these 2 left and right epipoles. And what is the condition that these are actually epipoles of some fundamental matrix that relates these 4 points? Well, the condition is that these 6 points lie on a conic. Okay, and so actually, we sort of know similar characterizations for 5 points, 6 points, and 7 points, of course. There's that's just the 7-point algorithm. So it would be nice, and hopefully someone this week can make some progress, to tell us a little bit about the calibrated case. So here it's interesting when we have at most 5 correspondences or matches, same thing. And there are some things that we already know, but it would be nice to get a complete answer like we have in the uncalibrated case. Okay, so I'll wrap up. I think we're all hungry. So there are a couple other aspects of algebraic vision that I don't have enough time to really get into, but I wanted to talk about things other than P3 to P2 cameras. So there's also this issue of what you might call flatlander cameras. So here I'm using B1 and B2 to denote linear maps from P2 to P1. And so this came up in a recent paper that is joint with a bunch of people, so Agarwal, Connolly, Duff, and Thomas, where we're trying to basically relate the 2-view reconstruction problem for pinhole cameras to a projectability problem for flatland cameras. And so one of the main results, which we were a little bit surprised by, is that if you have an instance of the 2-view reconstruction problem, so given by 2m points in P2, then that has a solution with 2 cameras A1 and A2, if and only if there exists some flatland cameras B1 and B2, which project the 2 corresponding sets of points to the same points in P1. So to remember this, just think reconstruction if and only if projectability. And what's nice about this if and only if is actually the construction shows that the epipoles of the fundamental matrix for your 2 pinhole cameras are precisely the centers of these flatland cameras. So, so in other words, if you wanted to understand the epipoles of the fundamental matrix, you could sort of think 1 dimension lower about the centers of flatland cameras. So by analogy, if you wanted to understand constraints on camera centers for pinhole cameras, you could think 1 dimension up and start looking at linear projections from P4 to P3. And so we'd like some people to explore what are the different Grassmann tensors for these P4 to P3 linear projections. And then finally, there's also, from the title slide, there are linear projections from P3 to P1. So these have something to do with radial distortion. And I won't be able to explain it, but if you find Victor Korotinsky, who's in the audience, he can tell you a little bit about some work we did, which involved solving the reconstruction problem for radial cameras. And here, there's lots of tantalizing connections to literature in commutative algebra and algebraic geometry. So in fact, there's only one sort of Grassmann tensor for the radial camera model, and that's what's called the radial quadrifocal tensor. So this is a 2 by 2 by 2 by 2 tensor, so it lives in the P15, and it turns out that this is basically the same as what's called the image of the principal minor map. And people have studied what equations vanish on these radial quadrifocal tensors. And so I think Broden and Raines were the first to figure out that there were 718 forms of degree 12 that vanish on this radial quadrifocal tensor variety. And this was also studied by Stroopels and Len, but the paper ends with an interesting question, which is, do these 718 equations actually generate a saturated ideal? And as far as I'm aware, this has not been answered. So I'll end with that, and feel free to ask some questions.